So if you love neuroscience and you want to know how can you draw inspiration from neuroscience and use it for artificial neural networks, then Hopfield networks, which is a kind of associative network, is a thing that you might be interested in. And the generalization of Hopfield network is Boltzmann machine, restricted Boltzmann machine, and in general Boltzmann machine. And there are many other ideas and models in computational neuroscience, such as spiking neural networks, asynchronous spiking neural networks, which is really amazing thing, because in machine learning, in computer science, most of the time we are working on, for example, our neural networks is in feed-forward neural networks, it's synchronous networks. But biological systems, on the other hand, are asynchronous. So there are great resources about Hopfield networks. And I really like these two researchers. Everybody knows John Hopfield. You have seen his interview with Friedman. And also Kroothoff, which is he's a great researcher, and I like many of his articles, and so many of my slides are a combination of these two books. I summarize them so you don't need to read both of them. So the original approaches to modeling these biological networks came back to many years ago, and that is McCulloch-Pitts neuron, which you have a weighted combination of them and then minus mu I, and you give it a step function, and then it is updated like this, and you're all familiar with this. But the associated memory problem is very important. So it illustrates about the simplest possible manner, the way that the collective computation can work. For example, some of your neurons are active at the moment, and 1, 1, 0, so it's a pattern like this. And at the next time step, it becomes something else. Or you can imagine it as a two-dimensional thing. Some of them are 1, some of them are 0. And so the pattern changes until it converges to something that we call memory. For example, we have different patterns. We say we have different memories. For example, if for example, my mind goes whenever hears Professor Christopher Manning in Stanford, then it converges to something else, for example, natural language processing, or the beauty of artificial intelligence. So it changes. It's like a dynamical system. It changes until it converges. And that's why 2 years ago I said human mind is a Markov chain, make it ergodic. So this is the associative memory problem. We could, of course, do it serially in a conventional. So this is the Hamming distance. We want to see how these two patterns that I said are similar to each other, because after all, they are just a bunch of 0 and 1. At the moment, we just model them discretely, but we will generalize it to the continuous case as well, which is more closer to the biological counterpart. So we look at a small region of an image, and then our mind can generalize. It's like a generative model that we use in restricted Boltzmann machine. Or here we can generalize it, because our neurons, some of them are 0, some of them are 1, some of them are active. It keeps changes until it converges to something that like this. So in biological networks, they call it attractor networks. Attractor networks is like Hopfield network. And the associated memory problem we transform to a formulation where the activation values of units, Wix will call it 1 if it's firing, -1 if it is not firing, instead of just 1 and 0. And then it looks like this. So again, we have a sine function, and our brain, as I said, updates asynchronously. But most of the machine learning, deep learning literature is synchronous. So we are losing lots of opportunities. That's why our AI cannot model infinite amount of memory, but the brain can model infinite, almost infinite, because it's continuous, and it is uncountable. And so you have infinite amount of memory inside your brain, but you don't imagine. You say, how can 80 billion neurons represent infinite amount of memory? But if you learn about asynchronicity, asynchronous spiking neural networks, you will see how the brain associative memory works and how you can do it in action. So one toy example is that we just assume that we have just one. The simplest case, there is just one pattern. We want to memorize it. So we just, if we just take the weights to be KCI times KCJ, because KCI, KCJ, for example, to have two neurons, I and J, so the weight of them is like this Hebbian rule. And so this toy problem, after some time, it converges to this attractor. And in general, we can model the weights as a superposition over many patterns, not just one pattern. So P here is many patterns. So we have different concepts in our mind. If each word, for example, represent one concept, another word, so we know several words. For example, we know 10 words in our brain, so we have 10 patterns, because our brain needs to memorize all of these patterns. So in general, we can have many patterns. So the second term is crosstalk term. We can conclude that the pattern number, this nu, was stable according to this formula. This is true if the second term is small enough. If its magnitude is smaller than 1, it cannot change the sign and will still be satisfied. For example, consider this quantity. This is just minus Kc times the crosstalk. If C is negative, the crosstalk term has the same sign as the desired. So we consider purely random pattern. Oh, by the way, when we say we update a neuron, we just pick it randomly in Hopfield networks that I will explain in the next lecture, and then we do it. So it's not synchronous. And this is the distribution of crosstalk that I said. And that is why we use the term energy function. It's very important because we can prove that the energy of the system reduces as it is updated over time. As it is updated, the energy is reduced. So here I can prove that the energy is reduced. H prime is the energy after we change one of the bits of our state, not all of them, just one of them, just one neuron among many neurons. Then we will see that this pattern, the first term is negative. The second term is negative. So the energy decreases. So each time that the neurons update, of course it's asynchronous, we assume that we pick one randomly and we update it. So the energy at each time step is reduced. So we make sure, because the number of finite, the number of possibilities is finite, so we can easily conclude that it reaches to local minimum. It's just like Lyapunov function in nonlinear control system. We have a Lyapunov function. It's positive semi-definite. It converges, and then it converges to the minimum. Not necessarily global minimum, but for example, in Hopfield network, we have lots of local minimum. So that's a big problem. That's why we get around this problem by inventing some, for example, noise, or even make it continuous, like the one that I will explain. And if we sleep, you will see that our landscape sometimes like this. We have two local minima, and when we sleep, we are unlearning that. Because, for example, these two are very similar to each other, but one of them is more important. So we unlearn, so it becomes like this. But if you sleep too much, it will become like this, and you don't learn anything. You forget everything, and it's like you are dead. And so this is a spurious state. It's very important. I will explain it later.